us about yourself and
Uh,
a little
sure.
background?
So I'm a PhD student, hopefully almost completing PhD student. I'm now in my fifth year,
Oh, that's,
and I study in the electrical engineering department at the University of Minnesota. My advisor is Professor Sachin Sapatnekar,
yeah.
and my primary research interests lie in using machine learning for physical design. So not so much on the verification or front end sort of things, but the machine learning in EDA is the common aspect here.
Okay. Yeah.
And the way I was introduced to Verify was I was talking to my advisor about some other an IC CAD contest, and he said, "Oh, there's this also this from Sandeep if you want to try it out." And so that's how I was introduced to it, and that's how I started it.
Okay, that's fantastic. So just to give you a little background, I mean, I've spent many years of my life doing physical design. So I was running
Oh, okay.
a
Uh-huh.
a large group in Cadence many years ago doing placement, clock tree synthesis, optimization, what have you. Right? So
Nice.
tell us a little more about machine learning and physical design, because physical design is interesting. It's got geometric aspects and it's got electrical aspects, right?
Right. So maybe I can speak from my research. Mine
Okay,
has
yeah.
been primarily in the power delivery network aspect of it. So power delivery network IR analysis in the sense of IR drop analysis, electromigration analysis. And the other has been in synthesis. How do you build a PDN or a power delivery network that's correct from by construction that meets your IR drop EM requirements from scratch, sort of a thing. So I've been working on the Open Road project,
Okay.
and this as a part of that, I've been responsible for parts of the PDN synthesis and primarily the PDN analysis. So that's where the background comes from. And as a part of my research, I've been applying machine learning to these problems. So for that, there are geometric aspects of it, as you said. What's the power delivery network pitch look like? What does current map distributions look like? Power distributions look like? How do you synthesize a grid that's quote unquote correct? That would even remain correct right at the sign off stage because you do PDN at floor plan and you want it to stay correct even after sign off.
Right.
There to kind of predict what's going to happen at the next step and be correct right at the beginning. Um, so that's sort of where the idea comes from. And I've been familiar with CNNs, multi-layer perceptrons, GANs, and GCNs to some extent of late recently.
Oh,
So
wow.
this is where my background comes
So that's fascinating. So what you described, basically, IR drop prediction,
from.
and one of our customers has actually built a tool right on top of our platform. And essentially, what they've done is they've taken tons of data which correlate timing windows with IR drop and physical location on a block. And these things, as you know, when you simulate it, it takes 24 hours, 48 hours. So
Right,
they've come
right,
up with a model, and the beauty of DNNs is it can fit a function to just about any model. So they can predict IR drops with an accuracy of 90% at 10,000 times faster than simulation.
yes, exactly. I worked on something very similar as a part of my internship at NVIDIA, and I think there was a paper on it recently. It's titled Maverick ML for uh, ML aided vector IR drop analysis, and it's exactly along the same lines
Mm,
that what you mentioned.
okay. So do you see so you mentioned correct by construction, so there's probably geometric things about pitches and tracks and
Mhm.
layers and so on and so forth. And then there's a simulation aspect, then there's
Right.
a timing aspect.
Right.
Uh, and then you mentioned very interesting that struck me was CNNs. And then
So I think the first paper that I worked on as a part of my PhD used CNNs, and the idea is very simple. We use a CNN for uh, in the form of a classification problem for the PDN synthesis. So the idea is how do you really map this classical EDA word problem into into a known ML word problem, and then you can leverage all the research that's been there in ML to solve something in EDA, and it's something really exciting. So the way we did that is we defined what we call as PDN templates. And what that means is they're these building blocks of the power delivery network. And what the CNN says is this template, say template A, B, or C, template A goes in region 1, template B goes in region 2, template C goes in region 3. And the idea is the features of the chip, which would be the dish, the cell placement, the power of each cell, form features that go into the CNN, and the CNN then decides one class, or a class as in a template, of which template goes into which region. So what we did there, the key aspect of that paper was the mapping between the EDA word problem and the ML word problem. You made EDA into a very classical ML word problem that's already been solved, and you can use this, and CNNs work well with images and classification, and you can use this to sort of synthesize a PDN.
Excellent.
So that was where this
yeah. Basically, you're taught graph algorithms. The whole crux of everything is graph algorithms. So now, how do you view it now when machine learning has come in so close that can replace a lot of the heuristics and things like that? What is your feeling on that area?
I think,
or the combination of the
graph algorithms still have to stay, right?
Yeah.
Because you need to know where you're like what's golden and where this entire field comes from. And I think even if we're looking at maybe 10 years down the line and we're looking at a whole GPU accelerated EDA flow, which uses machine learning to be correct by construction, I think the graph still has to stick. You have your netlist in the form of a graph, and there have been a lot of recent works that use GCNs that kind of mix the original graph algorithms with ML to do to solve really difficult problems that actually haven't been solved before.
Right. So graph neural networks. That's sort of a topic of interest. So then the other topic I just want to cover quickly and get your thoughts, since you're just coming out and your PhD and you're going to go conquer the world. If we see the last few years, there's a fantastic article by Andre Karpathy, right, which he talks about software 2.0, which basically says software 1.0 was all about rules, if then else, right? And if you couldn't solve if then else, then you came up with some heuristic to break out of it, right? So all NP-hard problems are heuristics, and and that's sort of the crux of EDA. Now, what he's saying is the new paradigm is these little machine learning models, which he calls software 2.0, that at least in Tesla, where he works, is slowly eating into the rule-based software 1.0 models, right? So what that means is, instead of a heuristic, you use a DNN, that's a function approximator, and over time it learns, right? So any feelings and insights from you as a fresh PhD graduate on these two paradigms, rule-based versus purely machine learning based?
I see. I guess it comes to where you apply it, right?
Yeah.
Purely using machine learning. So say I'm thinking completely from a physical design perspective, because that's where I can think. But so say you're applying ML at an early stage of the flow, right? Where you anyway have everything that's approximate already. Nobody knows what's the true power numbers of a design and say floor plan or placement. And at that point, when you want to get an approximate estimation of say your IR or say, is this good enough for EM? I think ML fits in there perfectly and you get it very fast. Say you want to do IR drop aware driven placement, right? You cannot afford to have a really difficult, a really time consuming simulation within each iteration of a placer, for example. So approximate would help. So I think in the initial stages of the flow, when anyway your numbers are quite approximate, ML would be a very valuable aspect there because it's fast and it's approximate, but you don't need that much accuracy. But when it comes to something that's really critical, maybe you're trying to run timing analysis on a,
Yeah.
this is, I need it to be as accurate as possible. Do I see ML there? Maybe not right now, but I don't know about how useful
Yeah.
it's going to be in the future.
Yeah. No, great. That's a great point because we've gone through this with what was called statistical timing analysis, where you, instead of giving a number,
Right.
you give a distribution. The problem
Distribution.
with that is people didn't understand what that meant.
Yeah.
So, but the thing about neural nets, I think, is it can keep learning. It can keep learning and mimicking even a spice simulator, for example, or a static timing engine over time. And it can become as approximate as the simulator itself, perhaps, right?
Correct. Over time, given enough data, I think
Yeah.
we can think RL is one example where it just
Yeah.
keeps getting better with each and every run.
Yeah.
And maybe at some point I do see an RL performing exactly as to the data that it was provided with or trained with, for example, or it could even, if not now, it could have a potential of performing better than what the tools actually do.
Yeah.
You can model your reward function to be as complicated as possible, something that's is not very feasible in an EDA tool, and you could get fantastic results from RL as well.
So now let's shift gears to the real reason you're here, which is the DB challenge. And so I want to kind of get a few thoughts about how you felt, your experience, and then you mentioned that you didn't know much about the cache controller. So I'd be curious to see what you've learned since you participated in the challenge. And
so I still don't know much, honestly. I've just read the help page, and I know what what the reads, writes, what exactly is very basic understanding of what's happening. But with the DB challenge, what I learned is effort that goes in your end, but there's also some things that not on my control. For example, where I tried to recreate the score that actually got me the 146. I put in the same settings, and turns out I cannot get the exact same numbers again, right? Because there is some amount of randomness in the, that was very interesting. And I was trying to apply settings that worked on other problems that I seem to know of. For example, I've always used possibly encoder decoder kind of network, or a network where you have sort of a multi-layer perceptron that reduces in dimensions and then again increases up in dimension.
Sort of a funnel, like
Yes.
Exactly.
Yeah. So I know that these kind of work on certain problems that I've tried. So my first shot at this problem was, why don't I try those settings and see what happens. Initially, they were not very good. Gave a few different, tweaked a few more parameters, and then realized that it's actually that I was actually doing fairly well on the leaderboard. And when I noticed that I was doing fairly well, and there were people who were catching up, that's when I started working on it more. I don't think otherwise I would have spent much time on it.
Nice.
Other thing that I really liked about the DB challenge is the low barrier. I mean, the low barrier to entry. I think I mentioned that. Given that it was well set up on an app and I just had to press a few buttons, didn't have to download, sort of do a build scripts and have compiler issues and have syntax issues. I mean, not syntax, compiler issues, system compatibility issues. I was glad that I just got over all of that and just directly went to sort of optimizing the system. So the low barrier to entry was what got me started, and sort of the competitive nature of that made me keep at it. So these are the two things that I really liked at it.
Excellent. Very, very nicely said. So then you said the competitive nature got you thinking and it got you excited about competing. So what, in terms of, if you could describe to a machine learning engineer, what is it that you would do with the hyperparameters that we've exposed there? What is it that you did, and what kind of worked, and what was your thought process?
So, uh, I started with what I knew would work at another problem. So, and I did not have much computer architecture perspective. So my initial uh, like brute force method was just set all those parameters to the midpoint, because I don't know what's supposed to work
Yeah,
on the computer architecture perspective. So just set all the reads, writes, everything to the middle of the range. And then let's work on tuning the hyperparameters, because those are some things that I understand better than the others. So that's sort of what I did. I still don't know if what I did was the right approach or not. But so then I went with the ML hyperparameters, and that's where I knew that I could do something that I understand. So I started playing around with different optimizers. The fact that I could see other people's settings that got them those high scores helped me significantly too. So I first set up those ML hyperparameters to what I think would work based on other problems. And then I started optimizing it further. Once I got a good result, I saved that model and then kept tuning more beyond that.
excellent. And in this scenario, would it have helped if you had, let's say, we popped up a Jupyter notebook and you could have built your own model, taken it further?
Definitely. So I think getting access to a few other things like in Jupyter Notebook, where I can sort of break the flow wherever I want to, because I tried to cancel it in the middle of an optimization and I did run into an error, and I was not sure, but then I emailed the uh, uh, VerifAI team, and they were helpful to get back. But I think a Jupyter Notebook to kind of tweak certain other parameters and continue uh, with the. So for instance, what I do typically is I more with my experience in ML is I change the learning rate significantly during iterations. So say
Right.
I'm running 100 epochs at a 0.01 learning rate. I change that at the 50th iteration. I exponentially decay the learning rate. But here I wasn't sure what's happening
Okay.
with
So
the
you,
learning.
so if I'm
With
understanding you correctly, you would create a checkpoint, save the
Correct,
model,
save the model and then
change the
reload
learning
and
rate.
then run at a different. Yes. So
Very
that's
nice.
something that I would do. And I think the only models we could do were multi-layer perceptrons here.
Yeah.
But I think I would definitely like to try something else.
Something.
So if it's a multi-layer perceptron, my understanding is there was no
Yeah, there's no
uh,
correlation.
convolution happening. So I think I would definitely like to try a little bit more complex model. I would like to see it overfit and then make the model simple, and then simplify the model a little bit.
Okay, that's a great strategy. Okay. So you mentioned that you learned a little bit about maybe design verification and cache control. Did you learn anything about machine learning from your experience on the challenge? And
Um, Not so much,
not
honestly.
so much.
Yeah.
Is it because
Um,
it was just packaged and only so much was exposed?
Correct. To me, it seemed like I was just tuning settings of a black box.
Yes.
And I think I wasn't able to get into the details and see what's happening.
Yeah.
Maybe I'm not sure if the back end was a tensor board or a PyTorch system, but if I could
TensorFlow.
get if I could get access to tensor board and see what's happening with the weights of the model, that would be another
Yeah.
thing to give me some more insight.
Yeah.
Uh,
Yeah. So the
So
idea, yeah.
honestly, on the ML front, I don't think it was. I don't think I could apply my ML knowledge, but benefit was not so much.
Mhm. Right. So if I look at conversely, the reason we set it up like this was to
Mhm.
make ML just a few buttons, right, for the domain expert.
Correct,
So that
correct,
so that kind of lines up with our thought process. Yeah.
correct.
So what would you like to see in the future from a so you're a physical design ML researcher, and you probably I would assume you're going to join industry, or is that assumption not correct? or
Not so much.
academics? Either way.
Okay. I mean, I don't know yet.
Yeah.
I'm keeping both my options open.
Okay.
So
Yeah. So
yeah.
given that you've spent 5 years in physical design or 4 years in physical design, I would assume that this is where you would take your research and also
Mhm.
do probably combine it with machine learning, since you're now an expert, I would say. What is it that you would like to see, perhaps from Verify, if you were to put up another challenge? And I know you said you want to see something in physical design. Uh, so any thoughts on that? And I'll give you a few parameters of what we've noticed. So one is sort of what could help collaborative innovation. That means many people working on one problem. Like you said, you went and looked at somebody else's hyperparameters. That gives you a little inspiration. So if you could map that to a physical design problem, uh, maybe you can state a few that are close to your interest. Uh,
Um, so I think a lot of physical design revolves around timing, right? Like I think that's the biggest piece of the puzzle in physical design. You have timing at every single stage of the flow. I've been looking at this myself, but I'm still trying to find out how there have been a lot of papers that use ML and GPU accelerated timing. But if, for example, we could get ML as into I mean, if we could get timing into an optimizer, which is set up like an ML world optimizer. Like for instance, what I'm getting to is, say we're doing a timing driven placer, for example. If you think about it, it's just an optimization step, but with the timing engine running at every iteration, right? At every iteration of the placer, you have a call to the timing analysis.
right.
In the same way, training a machine learning model is very similar to actually running an optimizer. And I'm not sure if you're aware of this paper called Dream Place.
Yeah.
Essentially draws analogies between uh, placement and training an ML model. It uses the same machine learning framework to actually perform placement and not having to, and there's no need to write placement code from scratch. So for instance, in their placer, they use wire length as an optimization. And instead of using a loss function for the machine learning, you just replace it with wire length. And then your weights essentially are the location of each of your cells.
Right.
So there's a very one-to-one map between an EDA algorithm, which is an optimizer, and a training machine learning, which is also an optimizer.
Very nice. Yeah.
So that's one thing that I've been looking at, and the key challenge there is actually making timing analysis a part of the loss function.
Yeah.
Right. So because it's non-differentiable nature, you have calls to look up tables, you have calls to you have a max operator there, which makes it non-differentiable. But there are approximate ways in which you can make this timing analysis differentiable and get it into a model. So it's a far-fetched challenge, but to have some amount of ML, because you can use it as an approximate estimator at different places. Timing aware, I mean, IR drop aware timing analysis is another one. Most of these analysis tools, IR, EM, power estimation, I think are a potential to speed up, but may not be as accurate. But I think there is a space where you can make it 1000x faster with a 90% accuracy.
Yeah, yeah. So I think to kind of summarize your point, which is very nicely stated, is if we could map and look at loss functions in other domains, then everything falls into place. All those if then else.
They all become an optimization problem.
Becomes an optimization problem. So
yeah. And the fact that you have it set up in ML or in a complete PyTorch or TensorFlow backend means you have it GPU accelerated already. Yeah. So that's kind of
very nice. Yeah. So this could apply to, I would say, let's say partitioning, right? I mean,
correct.
Something like that. Yeah. Okay. Okay, that's great. And then from a machine learning point of view, what do you see the challenges? I mean, if any?
Right. So the kind of the non-deterministic solution in
Yeah,
machine learning world, right? You run your training now, you get 90%. The next time I run it, I'm at 85, and
right.
I don't know what went
Right.
wrong. My everything was the same, right? So I think that's the biggest sort of a challenge that I see.
Yeah.
Model trained, your inference, given the same inputs, your outputs are going to be the same. Your inference is deterministic, but I think training to some extent inhibits the non-deterministic nature
Understood.
inhibits progress. Yeah.
So would you go as far to say that, yeah, we need to verify the models as well, right?
Mhm.
You need to bound it somehow.
Yeah.
That was very, very insightful, and congratulations on winning the challenge. Now I understand why you won. You brought
Oh, no.
some insight. You brought,
I honestly think there was a lot of luck because I tried to
yes,
recreate the 146 score and I couldn't.
yes. So that's the stochastic nature of the problem, but yeah.
Yeah.
Uh,
Yeah.
okay,
Yeah.
thank you very much, and then we'll be in
Yeah.
touch with your uh, Apple Watch. Congratulations
Sure.
on that, and we're
Sure.
probably going
Thank
to
you.
ask you a few questions about size, color, whatever
Oh,
else,
sure.
and
Yeah.
we'll have that out to you. So,
Okay.
okay.
Sounds
Any
good.
uh, any uh,
Thanks.
any questions for me or Vikramaditya?
Yeah, actually, I was looking forward to the physical design challenge. I noticed there was something on those lines on the website, but I'm not sure what that's about or if that's in the near future. Or
Yeah. So in the near future, the next challenge we're going to have again is a DV challenge, and I would encourage you to participate. And this is more of a more realistic, real life challenge. It's on a RISC-V microprocessor,
Mhm.
and just like here, you're trying to increase the FIFO depth. In the RISC-V microprocessor, we're going to try to increase what's called the victim buffer count. So victim buffer is again similar to it's sort of a cache coherency issue
Mhm.
where a victim cache line is a cache line that's been invalidated. So you call it a victim. So it's a very hard condition to fill up this victim buffer because many things have to happen: reads, writes, conflicts,
Mm.
memory address
Mhm.
conflicts.
I see.
So now we're putting it into a real life workflow, which is a RISC-V microprocessor, 64-bit, with an instruction generator that will generate these instructions. And the machine learning will create a model that tunes what instructions to generate
Mhm.
such that you get a very high victim buffer count.
I see.
So I would encourage you to participate in that. And then the
Sure.
next thing is, we'll think of some physical design problem. Yeah.
Sounds good. Sounds
All
good.
right.
Yeah.
Thank you very
Thanks.
much. Good luck with your
Thanks.
PhD, and we
Thanks.
hope to be in
Really.
touch.
Yeah. Sure. Thank you so much.